In this video, I want to talk a little bit about how saturation works, because we found some interesting things that I haven't seen on most of the websites that talk about this. So if we look at a saturation simulation, one of the first things that people often try to do is wave shaping. And we'll talk in just a minute about what wave shaping is. But I think the core idea with wave shaping is that we're trying to model a balance between the input volume and the output volume around some kind of clipping stage, which could be a tube or a transistor amp, an op amp, or a diode stage that's causing some kind of distortion or overdrive in the audio. And if we model that, typically we model it with wave shaping. So if you buy vacuum tubes, the manufacturer of the tubes often produces these documents that show a graph with a curve that show if you put in this many volts, then this is how many volts you'll get out. And it's not linear, meaning that the more you put in, you don't necessarily get, like if you put in twice as much voltage in, you're not necessarily going to get twice as much volume coming out. It sort of tapers off softly at the top end, and there's a limit to how much you can get out through those things. And so that's the idea behind modeling those using wave shaping, is that we're going to look at those functions, which are things we can measure, and they're relatively well known, and then we'll just come up with a mathematical function that has a similar shape. And it turns out that it doesn't even need to be exactly right, because there's a lot of difference between even one tube and the next in the same batch. So it's quite easy to model those things. Unfortunately, that's not the end of the story for amplifiers. One of the things that I've recently been impressed with as I've been investigating saturation is how important is the power supply. So if you look, as I said, if you look at the data sheets for a vacuum tube or a valve, if you come from the English side of the pond, that we do have this sheet that tells us what function we should use to emulate that. But there's another effect which I consider to be more important, in the sense that I think the second the power supply effect is actually where I think the really key part of what people like about tube amp sound is coming from the way that the power amp feeds the tube. But that's not what I'm going to talk about in this video. I want to just talk about the wave shaping side, but I needed to talk a little bit about the sag, because some of these wave shaping functions I'm going to show you have something to do with sag. So let's have a look at the mathematics for those of you who love maths. If you don't love maths, don't worry. You don't have to look at any of this. We're going to have graphs, and I hope they'll be easy to understand. So the first wave shaping function I want to talk about is a polynomial wave shaping function. And I'm looking if I've stated the function simply. I have it here. It's 3/2 times x minus 1/2 times x to the third power. And I've plotted that here. And then the polynomial wave shaping function goes from -1 up to 1. And then once you reach this limit at this corner, then we switch over to just cutting the signal off hard at the top and keeping it constant at 1. So let's talk about, for a moment, about what this graph is. So I don't know if you can read this, but there's a tiny little word here that says input, and there's one that says output here. So this x-axis of the graph represents the input, let's say the input voltage or the input current. I'm not sure which term is more accurate, but let's just generalize it and say it's the input. So what this graph is showing us, let's not look at the lower left corner. Let's just look at this, focus on this region here for now. So this is the 0 point, and we're seeing that if the input is 0, the output is also 0. And as the input increases, the output increases accordingly up to a certain point, and then you see that it's sort of curving down, and you reach this point up here where the input can increase significantly and the output doesn't increase very much. And then when you reach here, you can see that after the input reaches 1, which is just 1 unit in this graph, but it could be 1 volt or whatever your unit of measurement is, after the input reaches 1, the input can continue to increase and the output never goes above a value of 1. So this is clipping the input signal. And this left half of the graph is showing that it does the same thing on the negative side for negative values inputs as it does for positive values. Now if we're looking at vacuum tubes, this is not accurate. They wouldn't handle the negative side and the positive side similarly. But that's probably a topic for another day. Typically a tube amplifier, if it's a class AB amplifier, would rectify the signal. So one tube is going to handle the positive side and one's going to handle the negative side. And so you can ignore this. That's why we're ignoring the bottom part of the graph, because a single tube would only process one side of this. Down below I have an example where I'm putting a sine wave in, and the sine wave is drawn in orange. And then I'm showing the output of this polynomial clipping function drawn in blue. So right now I have the gain, this is my gain control, and I have my gain at 0 dB, which means it's not boosting. It's just taking this orange signal and running it through the clipping function. And you can see that this polynomial clipping function has boosted the volume a bit, and then you can see it got somewhat flattened out at the top. And that's right now I'm not pushing any gain. This is just what you'd get if you just turn the gain knob down to, not to 0, but let's say to unity, where the input volume and output volume are relatively similar. And let's look at what happens as we push the gain up. So I'll open this so you can see the decibels, the value in decibels. Here I'm at 2.2 decibels gain boost. I'm at 3, 4, 5, 10, 13, and here's 20 decibels of gain boost. So you can see with 20 decibels of gain boost, we've almost got a square wave from this polynomial clipping function. And so this would have a very high gain sound if you were using this as a distortion function in an amplifier simulation or a pedal, overdrive pedal simulation. And so in order to get this to clean up, you really need to keep the volume down in this around 0 dB. If you're anywhere, you don't really have to go. You can see I'm only 7 decibels of gain boost, and already it's clipping quite hard, even though this is technically considered a soft clipping function. So that's the first one. Now I want to go to a second clipping function, and this is a hard clipping function. So what this one does is it just takes the input signal and gives us all of that exactly as the output. So you can see here's about 0.5 on the graph. If the input is 0.5, the output is 0.5. If the input is 0, the output is 0. If the input is 1, the output is 1. But as soon as you go above 1, it clips with a very hard corner like this. So this is probably the simplest clipping function. And let's look at what this does to a sine wave. So if I have the gain down at 0 decibels, it does nothing. It gives me exactly the input and the output overlap, and you can't see the blue line. But as I boost the gain, it boosts, and then it cuts the top off flat. This kind of hard cutting is something that, first of all, we don't usually see in electronic circuits. Even the really, really harsh clipping that you can get from diodes, sometimes they're not this harsh. So this kind of clipping is something that we wouldn't usually want to do in software. First of all, it would cause an enormous amount of aliasing, and that would be difficult to prevent and difficult to remove. And secondly, it doesn't sound much like any electronic circuit because this corner is just too sharp in a very unnatural way. So here I am at 4.5 decibels. I'll just boost the gain up so we can see what happens to this one. And at 20 dB, I have almost a square wave with an extremely hard corner. Let's compare that back against what the polynomial soft clipper does at 20 dB. It's interesting to note that this is a soft clipping function, but if you compare this with this, they don't look very much different, and they won't sound very much different. Which is why I've seen there's an enormous amount of different ideas about which polynomial function we should use here. So I'm using this, as I said before, using this, but there are many, many, many different ideas about other polynomials you can use. And I personally find this a little bit of a waste of time. And I say it's a waste of time because you change any function you want in here, it'll change the sound a little bit, but by the time you put 20 decibels of input gain, they're all going to do this, and they're all going to look the same. So to spend a lot of time thinking about what this function should look like here when the gain is below 1. This isn't 1 dB, this is 1 meaning unity, so it's 0 dB. To spend a lot of time thinking about what your clipping function is going to do when you're not turning the gain up is a waste of time, because as soon as you have a clipping function, the whole point of it is you're going to turn the gain up, right? So it's important what these functions are doing when you're pushing the gain, and that's what we really need to care about. And for that reason, I don't use polynomial wave shaping functions unless I'm trying to. No, I don't use them anywhere in any of our apps. I can't think of any reason why I would use one of those, except in a rectifier. I do use it in a rectifier. So let's go on to the next one. Hyperbolic tangent clipping function. This one is very popular for several reasons. First of all, this doesn't suffer from the problem I mentioned before, where above 0 dB of gain, nothing's happening. It's just cutting the top off flat. You can see this has a very gentle slope, and when you put 1 dB of gain in, it's not giving you, when you put 0 dB, let's say 1 unit of voltage in, it doesn't give you 1 unit out. So this hyperbolic tangent function is actually taking your gain down a little bit, and so you'll need to compensate for that by turning the gain knob up. And then you can go all the way up to 2, and you can see it still hasn't, even at double the unity gain, which is a 6 dB gain boost on the input, it still hasn't maxed out the output. So you've still got headroom after you do a 6 dB boost. There's still room to do other things. So let's look at how this responds. So here it is. When I'm at unity gain, it's actually cutting my gain. And then as I push the gain knob up, this thing will come up with a very gentle curve, and it doesn't look flat on the top like the ones we've previously seen. And as I go up, I'm going to take it all the way up to 20 decibels. And even when I hit 20, it still has a nice curve here. So I consider this function much better than any of than either of the two previous ones that we looked at, in the sense that we don't want to get into a situation where we're playing quietly and it's clean, and then you exceed some arbitrary limit and suddenly it's distorted. People want to have this kind of touch sensitivity where I can get a range of different distortion sounds out of this software amp model, and based on where I set the volume knob or how loudly I play, I'm getting a range of different outputs. However, talking about this hyperbolic tangent clipping function, which is very popular, I didn't mention the other reason why it's popular, is it's fast, because the hyperbolic tangent will be built into C++, and it might even be built into some hardware. I haven't checked that, but I have tested the speed, and it's very fast. So it's nice for that. It's fast. It has an ability to clip softly at soft dynamics, clip hardly when you push the gain a little bit harder. But here's where I have some disagreement about the usage of the hyperbolic tangent function and why I'm not using it in my own apps anymore. I was using it for a few months in a test version of our saturator. When I go up to 40 decibels of input gain boost, you can see I'm now getting something which looks pretty much like this did and very much like this does. And that's not necessarily to say we should never use the hyperbolic tangent as a clipping limiter, because any limiter you use, no matter how clever you design the clipping function, if you push enough gain at the input, it's going to turn into a square wave at the output. They all do that. And that's a good thing, because sometimes you want that really high gain sound, and this is how you get it. You push the input really hard. And it's nice to know also that when you're looking for that high gain sound, you don't need to worry very much what clipping function you're using, because they're all going to get you to this this shape that we see on the screen right now as soon as you put enough gain into them. Finally, I want to show you the function that I do use and the function that I like best for clipping, and I call it asymptotic limit. I'm not sure if there's a more well-known name for it. I have not seen, I'm sure there are people using this somewhere for guitar amps, but I haven't seen any articles on the internet anywhere or papers where I see people using this as a guitar clipping function. But I like it for several reasons. The first reason, if you look at the graph, you can see it starts out giving me 1 for 1. You know, if I'm down here at the very quiet range, so this might be at negative 10 dB down here. Then when I double the input volume, the output comes out the same. So I get a clean range down here. And then when I'm at unity input, I get 0.5 as output. So I'm losing 6 dB of gain as soon as I use this clipping function. But of course I can make that back just by turning the volume up. But what's really nice about this is that when you're at 6 dB plus 6 dB gain boost on the input, you still haven't even come near to maxing out the output. So 2 times unity is plus 6 dB gain boost. Just for fun, let's take this plot range out further. I'm going to take it out to 10. So this is what's really lovely about this function, is it guarantees that you will never go above 1.0. It never ever clips off, it never reaches a point where it clips off hard. I'm all the way out to 10 times unity gain, which is that 20 dB gain boost? And I haven't maxed out yet. I've still got headroom at 20 dB gain boost, but I'm also still getting soft clipping, which means that this function is giving me a range of different clipping tone, from clean to very light breakup to a crunch tone, all within about 20 dB of gain change. And I have to boost it even further before I'd see high gain tone, but you can get it. You can get a high gain tone out of any of these if you push it hard enough. And we'll do that here. Let's look at this is, okay, so the orange is the sine wave and the blue is my, this is the hyperbolic tangent. I need to change this. Right. Now the blue is my my asymptotic limit. So you can see when my gain is at unity at 0 dB, it's cutting the volume down a lot, and it's wave shaping a little bit, kind of warming up that tone on the low end. Here I am at 6 dB of gain, and I've still got lots of headroom, but I'm also clearly changing the shape. If you compare the blue against the orange line is the clean signal, the blue is the wave shape signal. It's changing the shape, which means I'm getting saturation, but there's a lot of headroom left. Now I'm going to go all the way up to 20 dB. That's right here. At 20 dB, I've still got headroom, and that's why I like this function. So I can go all the way up to 40 dB, and I've still got a little headroom left, and I'm still not quite into high gain amplifier territory, even at 40 dB of gain boost. So let's go up to 60 dB. Now I've got something that looks like what the other clipping function way back here gave me. Now I've got something like this. But even still, if you look at this corner here, it has this sharp edge on it, which is going to cause aliasing, and it's probably not going to sound the way we like guitar amps to sound. Whereas this one, it's straight on the side, it's straight on the top, but it still has a nicely rounded corner, which is going to reduce the amount of aliasing noise that I'm getting, which obviously we want to create noise when we're doing distortion, but we don't want aliasing noise. And you can look that up in another video we did 2 months ago, I think, about aliasing. And that's why I like using this function. There's another reason I haven't told you about why I like this particular clipping function, and that is that if you want to start simulating the sag that comes from the power the power supply being drained by the tubes. It turns out that mathematically this function, it comes out of that model. When you want to simulate that, you need to do this function first before you do the next stage. So not only is it having a lot of sensitivity to different levels of input volume, but it's also mathematically correct in the sense that a certain model that I've looked at causes this formula to pop right out of when you solve the equations. You get this exactly this formula. So for those three reasons, I find this to be an excellent way to do wave shaping. And the last thing I want to talk about is a comparison of all the clipping functions in one graph. So here we are at unity gain 0 dB, and you can see my asymptotic limit function is coming down with the lowest output volume. In fact, it's cutting by 6 dB compared to the input signal. What's the orange one up here? The orange one is the polynomial one. The green one is the hard clipping one. What? Almost done with the video, so I'm going to leave the bird here, even though he's probably hungry. And then the blue one is the hyperbolic tangent. So let's look what happens as we boost the gain. So as soon as we boost even a little bit, the hard clipping function gets these hard corners, which is something we would, I think we should say never. We would never want that to happen. And then at about 20 some dB, we see both the green and orange, which are the hard clipping and the polynomial clipping, are both starting to get those corners with hard edges on them. And as we get into high gain tone, as I said before, you want it to start looking like a square wave, but not with a sharp corner. And the hyperbolic tangent is now getting into a nice high gain tone. Like this blue line, which represents the hyperbolic tangent function, that would work nicely to give you a high gain tone. And the asymptotic limit function that I prefer at 20 decibels of input gain is still in like clean tone, but starting to break up. It hasn't got into high gain territory yet. And as we go up further, here's 30 decibels of input gain. At this point, it looks like the green and the orange, which are the hard clipping and the polynomial clipping, are not usable anymore. They've gone beyond their corner is too sharp, and there's going to be too much aliasing. They're not going to sound good. But the hyperbolic tangent is still okay, still useful for a high gain. And now we're seeing the asymptotic limiter getting into crunch territory. And as we go up further, now the asymptotic limiter is getting into high gain territory, and the hyperbolic tangent limiter is getting to the point where I probably shouldn't use it anymore because it's going to generate aliasing. And let's go up a little higher. By the time we get to 60 decibels of input gain, this asymptotic limiter is still having nicely rounded corners, but the sides are straight up and down almost, and the top is flat. So this is the only one that's giving me high gain tone at 60 decibels of input gain, and not clipping these corners so hard that I'm going to get unusable aliasing. I don't want too much criticism on the hyperbolic tangent because it's a useful clipping function. But I did this video just because I want to get this function. So this is, your input is x, so you're taking the input divided by the absolute value of the input plus 1. I want to get this out there because I think this is the function that you want to use if you're making a saturator. And once again, if you just do this, it's not complete because you haven't got the sag model in there yet, and that's important for the touch sensitivity, but also to get a little bit of compression on the tone, and to get it to sound like a real amp. It's important to have that. But this is the starting point, and I think this is essential to getting a software amp tone that responds well to a lot of different volumes. So that is, I think, a good point for us to stop and end the video. And if you enjoyed this, hit subscribe. Then the next time we do a video, it will be prioritized in your YouTube feed. Also, if you enjoyed it, please hit like, because that'll help us grow our channel. So I'll see you in the next video, and have fun working with this stuff if you are working with it. If you haven't been working with this stuff yet, check out some of the videos we did earlier this week about modeling guitar tones, because there's a lot of stuff you can do there by yourself, even if you're not a computer programmer and you're not doing plugin development. We talked about some things that you can build, some amp models that you can build just using standard plugins like EQ and saturation. And those are things that I think anybody who has a digital audio workstation can start playing around with.